In this video, we're going to discuss the hyperbola. The hyperbola is a conic that's formed by intersecting the cone with a plane at an angle such that both halves are intersected. So we have the top half as well as the bottom half that is intersected. And we can examine this. So we have the point of intersection will form two sections, and the two sections are unbounded curves that are mirror images of one another. Let's look at the standard form of the equation of a hyperbola as well as how the hyperbola is constructed using the foci. The hyperbola is a set of all points such that the difference of whose distances from two fixed points, the foci, is a positive constant. This is very similar to the way that we form an ellipse, except for the ellipse considered the sum of distances, whereas here we have the difference, or we must subtract the distances. It is worth noting that the hyperbola can open up or down, or left or right. So given our axes, x and y axes, we have two vertices of the hyperbola. So this is for an example of our hyperbola opening left or right. If these vertices occur on the x-axis, we would label them as minus a, 0, and positive a, 0. Each of these sides of the hyperbola also have a foci. We can label these as F1 and F2, which would be point C0 and negative C0. And each point on the hyperbola will have a constant distance, and we'll call these distances, so D1 and D2. So the difference, D2 minus D1, will remain constant for all points on the hyperbola. Let's examine some key features of the hyperbola, and we'll draw a hyperbola in this case that opens up and down. This hyperbola will have vertices. When it opens up and down, your vertices appear on the y-axis. There's also co-vertices, which appear on the x-axis, and we can consider a rectangle. I'm drawing it in dotted lines because it isn't part of our graph. What this rectangle provides us with is the means to write or to draw the asymptotes of our hyperbola. So asymptotes are lines or regions where our graph will get very arbitrarily close to, very close to, but never equal. So I'll label these as asymptotes. We also have foci, which we can label on our graph. We can calculate the coordinates of the foci based on the original formula. So although they're called foci, if we're referring to both of them together, individually they are called focus points. So now it's time to draw our hyperbola. The hyperbola will get arbitrarily close to our asymptote, go through the vertice, and we have two portions of the hyperbola, one above the x-axis and one below the x-axis. Now the axis that connects the two vertices is called the transverse axis. The axis that connects the co-vertices is called the conjugate axis. All of these key features are also present when our hyperbola opens left and right, and they are all identified in terms of our A and B values in the table below. The standard form of the hyperbola with a center at 0, 0 is x squared divided by a squared minus y squared over b squared is equal to 1, or y squared over a squared minus x squared over b squared is equal to 1. So notice the difference between the standard form of a hyperbola and the standard form, the equation of an ellipse, is that we have a minus sign between the two squared variables. When the minus sign is in front of the vertical variable, our graph opens left, right, and when it's in front of the horizontal variable, it opens up or down. The foci are identified. Note that the formula to calculate C is different than with the ellipse. It's a sum of the values squared. We can calculate the transverse axis and the conjugate axis in terms of A and B, as well as the vertices. Finally, we have two equations of a line that define the asymptotes of the hyperbola. Make sure you keep all of this information handy when you proceed with the practice problems so you can refer back to the key features of the hyperbola. Before we look at some practice problems involving hyperbolas, I want to take a look at some equations and determine what shape the graph would have based on the equation below. First, we have the equation 4x plus y is equal to 16. We only have variables that are to the power of 1, so x and y, and this would form a linear equation, and the graph would be a line. In example 2, we have 4x squared plus y is equal to 16. In this case, one of the variables is squared and the other is not, which means the resulting shape would be a parabola. And we can place this into standard form by bringing all the variables to the other side of the equation. You get minus 4x squared plus 16. It's worth noting that that would be a parabola with a vertex that is not at the origin, but we'll look at how to translate the axes in another video. Question 3, we have x squared plus y squared is equal to 16. This is the equation of a circle with radius 4. So we know that this is a circle or ellipse and not a hyperbola because we have the sum of the two squared variables. And also we know that it's a circle and not an ellipse because the coefficients in front of the x squared and the y squared are equal. Remember that coefficients are just the constant in front of a variable. For question 4, we have x squared minus y squared is equal to 16. Because it's the difference of two squared variables, we know that this is the equation of a hyperbola, and we can write it in standard form by dividing both sides of the equation by 16 And we get x squared divided by 16 minus y squared divided by 16 is equal to 1. So this would be a hyperbola with a is equal to 4 and b is equal to 4. And this hyperbola would open left, right. And last but not least, we have x squared plus 4y squared is equal to 16. Note that we have the sum of two terms with squared variables, and the coefficients in front of the two squared terms are not the same. So we have a coefficient of 1 and a coefficient of 4. This will be an ellipse, and we can write it in standard form by dividing both sides of the equation by 16, and it will reduce to x squared over 16 plus y squared over 4 is equal to 1. Therefore, it's an ellipse with a is equal to 4, b is equal to 2, and the major axis will be on the x-axis, and the resulting ellipse will be wide and not tall. Let's do some practice examples involving hyperbolas. Question 1 says, find the vertices, foci, and lengths of the transverse and conjugate axes of the hyperbola x squared over 144 minus 1y squared over 25 is equal to 1. And we want to sketch the curve. So here the positive portion of our curve is with x squared, and the negative is with the y squared. Therefore, the hyperbola opens left, right. We know the value of a is the square root of 144, or 12, and the value of b is the square root of 25, equal to 5. Using this information, we know that there are vertices on the x-axis at 12, 0, and negative 12, 0. The length of the transverse axis is 24, 2 times a, and it connects the two vertices. The length of the conjugate axis is 2 times b, which is equal to 10. In order to identify the foci, we must calculate c. C squared is equal to a squared plus b squared, which is 144 plus 25. Therefore, the value of c squared is 169, and c is equal to 13. Therefore, we have foci at the following 2 points on the x-axis, so 13, 0, and negative 13, 0. Now let's make a sketch of this graph. Another thing that we could have calculated was the equation of the asymptotes, but we weren't asked for it in this case. It is helpful to sketch the asymptotes to make an accurate graph of the hyperbola. So we have the vertices at minus 12 and 12. And we have the co-vertices at 5, minus 5. And we can draw the foci, which is at 13, at negative 13 and 13. If we identify the corners of our rectangle that could be formed by connecting the vertices, we can sketch the asymptotes. Should be straight lines. Make sure that if you're doing it by hand that you use a straight edge to connect these points. And our hyperbola, I'm just showing the vertices there, we'll get arbitrarily close to the asymptotes but never touch them and pass through the vertex. And that's a graph of x squared over 144 minus y squared over 25 is equal to positive 1. Question 2 says to find the vertices, foci, lengths, and transverse and conjugate axes of the hyperbola y squared divided by 16 minus x squared over 9 is equal to 1. Notice in this case our hyperbola will open up or down. The positive portion, the positive squared term is the y variable, and the negative is the x variable, therefore it opens up, down. So we know that the values of a and b would be 4 and 3 respectively. Therefore, our hyperbola has vertices at 0, 4 and 0, negative 4 on the y-axis. We can identify the lengths of the transverse and conjugate axes. For the transverse axis, it's 2 times a equals 8, and conjugate has a length of 6, which was found by multiplying b by 2. Now we need to calculate c, given that c squared equals a squared plus b squared, and that is 16 plus 9, or 25. Therefore, c is equal to positive 5, and we have foci at 0, 5 and 0, negative 5. Now take a moment and sketch this curve that opens up and down and compare your work to what's written here. So here we have the graph of y squared over 16 minus x squared over 9 is equal to 1. And we can see the asymptotes as well as the vertices, the foci, and the co-vertices of our graph. In the next video, we're going to look at translation of axes. So we'll take all the conics that we've looked at already and show them with a different center or vertex than at the origin.